let's talk a bit about composite functions now. So what a composite function actually is it's a function inside of another function. And what we can do with that is, so remember we talked about our function notation before and how I talked about an f of g of x. So another way to write this as well is just fog f. So what we have here is this, and we can also write it as fog as well. Gosh, why the pen like that? Yeah, so we can also write it as fog as well. This is really, really thin. Why can't it be thicker? That's right. That's fine. So you can also write this as fog or F-O-G. Well, that's better. Why wasn't it working before? So yeah, you can write it that way as well instead of this way. And I think that this one's actually the one published in VCE papers now. So what actually happens in a composite function, it's kind of like something going through two machines, like double deep frying your chicken, or deep frying and then wok tossing your chicken, or like just cooking it another way, or shredding your chicken, like cooking your chicken and then like re-majigging it when you put it into like a salad or something. Yeah, so what we're trying to do is we get something into a function, right? And then we get whatever's outputted from that function and put it into the outside function. So an important thing here, even though it might seem a little bit confusing, is what we want to do is kind of jug it along in terms of two types of trains. So what happens is we essentially will get it going from one function to the next function. And we can talk about it a lot more when we have the beautiful diagrams coming up in a couple of slides. Alright, so let's talk about trying to write down the rule of this, and I'll just pop this question into the chat. Okay, alright, let's have a go together. So write down the rule of f of g of x. So actually, before we can even write down the rule, when they ask you to find whatever, do whatever, the really most important thing is actually to figure out whether these composite functions even exist or not. So whether these composite functions exist or not is really important to find out first, because sometimes they'll throw in a bit of a trick question and have it actually not exist, which is really problematic. But it's a bit of a trick, especially for like SACs as well. It's a really big trick that they tend to do, because they're trying to trick you into trying to remember that for the actual question. Oh, sorry. Just make sure the screen looks okay. Alright, looks good. Cool. So what we're going to do here is we're going to have, so we'll talk about we can just kind of briefly talk about it in terms of making sure one function can be subbed into the next function, and then we'll talk about it again in the next couple slides, but let's kind of run through it on how we would do it together. So essentially what we want to do is, in order to test whether f of g of x is possible, what we're trying to say is the outputs of g of x possible to be substituted into the inputs of f? Now, why this for this function is very unproblematic is because the domain of this is R. So as soon as you see that the domain of the outside function is R, and because we're working in methods, not spec, there's not really anything bigger than R that really can be subbed in. So we probably don't need to investigate further than that, because we already know that the domain of the outside function is R. So we don't really need to consider it further. But if it wasn't, we would have to look into what the outputs or what the range of g of x is, and then see if it fits it. Okay, cool. So in order to actually write down what the thing is, it's actually quite intuitive what you try and do. So you have f of g of x, and what you're going to do is literally just sub in the expression into there. So you're going to have of 2x plus 1 squared plus 1. So essentially, your g of x is replacing all positions that you have x in. So we have 2x plus 1 all squared instead of just x all squared. Okay, so what we're going to get here is going to be 4x squared plus 4x plus 1 plus 1, right? Which is equivalent just to 4x squared plus 4x plus 2, right? So you just simplify it right down, and that's what really you're going to get. Cool. Awesome. And then you can just leave it like that, unless they ask you to do a specific type of form. Alrighty. Okay. So, like we kind of talked about before, functions are machines, and now we have the beautiful diagram that we can kind of talk about together. What we're trying to do is essentially a composite function is just two machines back to back. So when we talked about h equaling to f of g of x, what we're having is just two machines back to back. So if we kind of look at this, what this actually means is that all of the outputs of g have to go into the f. So in order for this function to be a function, once again, we have this buddy system. So if it can't, it's kind of like trying to fit a square into a circle hole. Like, you know, all those games where like you had to like fit all the shapes into like the correct holes and stuff. Or like the saying that, you know, like one of those like real cute sayings about like you are the circle in like a whole like, I don't know, a whole group of like triangles or whatever. It's one of those things. So like, because essentially a square won't fit into a circular hole, what we actually need to do is manipulate into a circular shape so it fits through. Not great for talking about conforming, but you know, in the world of mathematics, unfortunately, we do have to conform to what we really need to do here. So what we have to do is change the stuff coming out of G to actually fit into what's coming to F. So i.e., what that actually means in terms is the range of G must be the subset of the domain of F. So range G, and we can use our symbol for subset, the domain of F. Alright. I like to also kind of just draw to really figure out what's going on here. We can kind of draw out, so this whole machine is going to be our H, but if we talk about our G and our F coming in here, so what happens here is we sub in the dom of G, and then the range of G comes out from there. And what we should be summing into here is the domain of F, right? We need this to conform to this. Now, if those two things aren't the same, what we're actually going to have to consider is how that changes the range of F. So if range of G is going to be smaller, as in there's less numbers, or it just like, say that was 1 to infinity and the other one was 0 to infinity, then it's going to change what the output here is. So the range of the overall function is going to be changed to something smaller. If the range of G is bigger than the dom of F, you're not going to have a defined function, and you're going to have to manipulate it until it actually fits within it. If it's equivalent, that's really the only scenario where you kind of just look at the two ends and you can get the domain of the range of the composite function. Otherwise, there needs to be some type of manipulation throughout the process. Okie dokie. Alright, so this kind of gives us an important thing of the real kind of summary of this is, in order for a composite function to exist, the range of G must be a subset of the domain of F. And that is a sentence that you can just regurgitate onto your page to kind of prove that it works or not works. Alright, so let's talk about this. So now we have similar functions to what we were dealing to before. Bit more complicated, I guess, but they're asking us whether both ways it exists. A really good method for doing this is, especially if they're asking whether both ways work, is to kind of do this table method where you list out, you kind of talk about what's the domain of F, what's the domain of G, what's the range of F, what's the range of G, and how you can kind of just set it up is something that, oh, let me try and draw this so it's a bit actually nicer. set it up so it's a bit nicer. Okay, so we can DOM range G F, right? So they've kindly given us the domains already, so we're pretty happy about that. So the domain of F is R as given here, and the domain of G is 0 to infinity as given there. Okay, cool. So let's talk about the range. So in order to find out the range of basically any function, or most functions anyway, the easiest thing to do is just graph out and see what it looks like. So in terms of what this one looks like, this one is going to be looking like this. So it's going to start from -1 and then kind of go up into infinity and beyond. So what we can say about that is it's going to start at -1, right? And go all the way up to infinity. Cool. Right. In terms of G, now let's look at G. So G is going to be a square root function, so it's just going to go that way. So you can see that it's just 0 to infinity. Alright, so let's talk about f of g of x first. So in order for this to exist, the range of g, so the range of the inside, has to be a subset of dom of f. So let's talk about it. So the range of g was for us 0 to infinity, and that in fact is a subset of R. So therefore, f of g of x exists. Right. Okay, let's now talk about g of f of x. So in order for this to exist, the range of f has to be a subset of the dom of g. Cool. So what that actually means is we're going to look for the range of f that's -1 to infinity, right? And the other one is 0 to infinity. And we can see that this is actually one step further than this one, so it's not a subset. There's actually a symbol for that, so let me draw the proper. So it's not going to be a subset, which we can kind of represent like this, right? So essentially it's not a subset of it. Often, so there you can say therefore g of f of x is not defined. Often a follow-up question, which is not asked here, but a really common follow-up question is kind of just asking, like, kind of make this, so how can we make g of f of x exist so it is defined? So it'll be, say something like restrict f of x so that g of f of x is defined. Okay, so what that actually means is now we have to say range of f now has to equal to 0 to infinity instead, right? Because it has to be restricted back. So then what we actually look at here is we go back to this and we say to ourselves, okay, what that actually means is now f of x has to just be bigger or equal to 0. So we can look here, and that's our 0 point, right? That's our line there. And the numbers here would just be 1 and -1. Because if we just made this equal to 0, it'd just be x squared equals to 1, so the x equals to plus or minus 1. So therefore, we can kind of see from here, if we need it to be bigger than 1, what that actually means is that it can be from anywhere from -infinity to -1 inclusive, because 0 is included, and then union with 1 to infinity. So essentially, the only numbers you can't really take is between -1 to 1. Ooh. And then you can just put that in, and then you can also work out, so in this one, the actual overall range, so the range of g of f of x is just going to be the range of whatever g of x is, so that's 0 to infinity, so we can just pop that in. Cool. Alright, so like we were chatting about before, if there is changes to, so if like this one, the range of f does not exactly equal to the domain of g, and then once we manipulate it, it's not exact, like for this one, it's unchanged, right? Because that is equivalent to that exactly. But if it was changed, we need to recalculate the new rule and the new domain. So what we do is we put in the domain, put in the new rule, and then kind of calculate and just graph it again. So what that actually means is that we'll also need to work out what the domain of f of g of x will become after it passes through both of them. So we kind of, once we do that, we kind of flip it backwards and see what domain changes had to do. So for this one, the new domain of g of f of x would just be negative infinity to negative 1 union with 1 to infinity. And then the range for this one would have just been 0 to infinity. Alright, so just like this, what we can do is we essentially have domain G, domain of range of G, and then we can sub it with what we're trying to do is we're subbing it into the domain of F, the range of F, right? Because that's what is kind of working out in terms of the function. So we just really need to be careful about what's going on here. Cool. And this next question kind of represents it quite well in terms of what we're actually trying to do. So we have these graphs of two linear functions, f and g, and we want to find the range of f of g of x. So what we're trying to do, if we kind of think back to our diagram, right? First, what we're going to do is try to sub in the domain of g, right? So we sub in the domain of g, that's negative 1 to 1. That outputs a range of g, which is going to be, so the domain of g was negative 1 to 1. The range of g is going to be 2 to 4. 2 to 4. Now, we have to check whether that works with the DOM of f. So the DOM of f is from 1 to 5. So therefore, you get the range of g is a subset of the domain of f. So that means that the function exists at least. But we note that it's actually smaller. So it's only from here to here. So that's the new thing you're going to sub into f now. So we're going to sub in 2 to 4 into whatever f to f is to get whatever that is. So we picked 0.2, pick 0.4, and for a linear function, for a non-linear function, it might be a little bit more complicated. For a linear function, you can just really pick the endpoints. For a non-linear, you just have to look whether there's any stationary points or any special points in between. But, oh, sorry about that. Go away. Alright, so what we're going to do is we can see that's going to be from 2 and that to 0. So that means that when we output that, we get 0 to 2. And that's going to be our new range. So it's going to be 0 to 2. And it does make sense because essentially what we're actually saying here is we can see, okay, this says a rise of 1 unit. So this goes from, if we talk about like a rise over a run, so that's 4 minus 2 over 1 minus negative 1, right? So that's 2 over 2, which equals to 1. And our y-intercept is that. So essentially this is y, x plus 3. And this function here, once again, we have from 5 to 1. So 5 minus 1 over, oh sorry, that's the domain part of it. Essentially what we have here is going to be 5 minus 1 over negative 1 minus 3, right? Negative 1 minus 3, yeah. So negative 1 minus 3 is negative 4, 5 minus 1, so you're going to get negative 1 here, and then y equals to negative x, and then if we kind of tried to pretend to extend this line, we would have an intercept of 4, right? Plus 4. So what we can see here is if we look at these two graphs and then pretended to kind of put them two together, what we would get here is that this would be equivalent to saying, so this is our f of x, that's our g of x. So we'll have x plus 3, negative x plus 3 plus 4. So we would get negative x plus 1, right? So we can kind of compare what we're trying to do here. So what we're going to sub in at the very start is negative 1 to 1. And what we're going to get is 0 and 2. So if we subbed in negative 1, we would have gotten 2, and if we subbed in 1, we would have gotten 0. So it kind of works out in the end.